Hello, principles of physics class. This is going to be a quick recording to review momentum, if I could spell review. So momentum. So some things that we have to understand before we can get, momentum, the symbol for it is lowercase p, and it's similar to inertia. The idea of object in motion kind of wanting to continue moving is what inertia is. But inertia is just measured by the mass. Momentum is measured by the mass times the velocity. I'm going to draw an arrow over the top because it's a vector. And the vector has, so this v vector has a magnitude, which we can call the speed, plus the direction. So it's really important that you keep track of the direction. Like, for instance, we're going to talk about collisions and one object going this way versus one object going this way, or these look like little toy cars, but this could be football players or lacrosse players or dancers that are out of control. If they are going in opposite directions, we have to account for that, and usually we do that mathematically with a plus or a minus. Okay, so this is how you calculate momentum. If we looked at F equals ma, and I know we did this in class, so I'll just do it again real quick. If we insert, instead of A, we insert the definition of acceleration, which is your change in velocity over your change in time. And then we kind of rearrange it. We cross multiply and bring the delta t over there. What you end up with is F times delta t equals m delta v. We affectionately called this MAV fat in class, or fat MAV. This side is the change in momentum, and this side is called the impulse. And we give it capital J for some reason. I am not sure why, but who cares? Okay, so this is a way to figure out, for a given force over a certain amount of time, how does that cause the motion to change? You can use this, to figure out how much force is there on your face when your airbag stops you. You have a certain change in velocity of your face over a certain amount of time, which it might seem like a split second, but it's definitely longer than, say, your steering wheel or your dashboard. So that's a good thing that time goes up. If you solve for F, it equals m delta v over delta t. If this number goes up in the denominator, that means your force is going to go down. So anytime in layman's terms, you use the words cushioning, essentially what you're doing is prolonging the time in which it takes to stop, which in that case will always cause a smaller force, which usually is a good thing. You usually want it to be a smaller force to not break bones and things like that. Okay, so that's MAV fat right there. So that's an important one. Your momentum is that. And just remember impulse versus change in momentum. The units, Newton times seconds. The units for change in momentum are the same as momentum. It's kilogram meters per second. There's no special name for it. And the last thing that I want to talk about, because I want to try and keep these videos brief, so if you are watching them, you don't feel like I'm wasting your time. The last thing is conservation. And I don't know if this small little box over here is going to be enough to cut it, but momentum is always conserved in collisions. That means you don't lose any of it. It's not created or destroyed. It stays the same, but it can change sort of forms a little bit. So if you look at my first example here, I'll kind of circle it in red. This first example of these cars colliding head on, I'll call this one M2 or M1 and this one M2. And let's say this one has a speed of 5 meters per second and this one has a speed of 2 meters per second. I can't leave it as 5 and 2. One of them has to be positive and one has to be negative. We like the right to be positive, so I'll make this car that's moving to the left negative. And I can give these numbers, I guess. These are toys, so 10 kilograms versus 20 kilograms. So if it's conserved, we know that the momentum before equals the momentum after. And the way we calculate the momentum is m times v. So I could say m1 v1, and I always want to add up because this is the total momentum. I want to add them up. So I do m1, v1, that's the momentum of car 1. I'll write it like this. P1 plus P2 is our momentum. That's before. And then I say, well, it has to equal the same momentum after. Now, I'm going to assume that these cars stick together. If they stick together, their mass is now 1. I just add the masses together and I multiply some by some combined velocity. I'm going to put a prime here to denote after. So if I do this, I'll get, 10 times 5 plus 20 times, and this is where you have to be careful, the negative 2. I left out my units because I wrote them up here and I have this really small box, but you should put in units. The total mass would be 10 and 20, so that would be 30 kilograms times some combined velocity. Now I can do the math on it. This would be 50 minus 40 equals 30 times V combined. So 10 equals 30 V combined, or V combined after is equal to 10 over 30, or 1/3 meter per second. So one was going 5 meters per second, one was going 2 meters per second in opposite directions. What they do is they stick together, and I'll pick a different color here, green. They stick together and they both go off in this direction. I know it's that direction because it's positive, at 1/3 meter per second. And you'll have sort of your two cars together there, stuck together. Okay, if they bounce, if they didn't stick together, you would just do M1, V1, and I'll put a prime for after, and M2, V2 prime for after. The problem with this is you need to know one of these two numbers after. You can't just solve for two unknowns. Okay, so that's in a nutshell our review of momentum. Under 7 minutes.